this video. Here we'll be finding the definition of or the rules of differentiation of how to apply to any powers of x here. So this should lead on to solving more difficult problems rather quickly and easily. All right, so here's the exciting part. There we go. So I'm gonna first of all remind you about some facts that we learned previously in chapter 8. Okay, because we do use this in the proof here, and we have kind of been using binomial expansion in for small powers of the x. Notice we actually never differentiated anything more than x cubed because using the binomial theorem is rather tedious. So notice that the first n choose 0 is always going to be 1, and then this n choose 1 is going to be n. After all the expansion, if you remember, you could have written n factorial as n times n minus 1 factorial, and this would have cancelled the denominator. N would remain on the top, and dividing by 1 would leave it unchanged. Okay, and then we look at the second coefficient there. Here n choose 2 will be n times n minus 1 over 2, and the third one almost the rest almost don't matter, but I'm showing you because is in year 13 we'll look in more depth at these parts. The later parts of the problem do matter for year 13, but we'll visit them later. For this part, we just concerned with the first couple of coefficients, really. All right, so I'm gonna rewrite these nice and neat because there's too much on that slide there. So what we learned is that when you're applying this, I've put the a there as well. So this a is just a constant, and that goes outside of the bracket anyway. So you don't need to be concerned about it. What you notice is that this we always subtract the function itself away, evaluated at point x. So the first term and the last term always cancel away. All right. So that's why, because that x to the power n is cancels away. Then on the next line we left with after this cancellation we left with the rest. Second term comes, sits at the front, and so on. And this is our last term now. Okay, and notice these delta x's start with the power of 1 and then go to, in the second term, have a power of 2, and so on all the way. We omitting those in the middle because we don't know actually the value for n. This is just the abstract theory. We don't need to know the terms in the middle. What you need to notice is that after the first factorization of delta x, only the first term here will have cancelled away without and left without a delta. So all the other terms have delta x's on them. So sorry, that would be now n minus 1. So all these delta x's remain. All right, only this very first term here, this a n x to the power n minus 1, has no, this very first term has no delta x in it. So when we evaluate this limit, this term and every other term will approach 0. Only this term remains, the very first term where you had this a multiplied by n. This is the format. All right, so we make a generalization about this. Okay, everything in between cancelled away. All right, so notice the shape of that. This down here, this is really dy, if you see dy over dx, it means the same thing. It means that we are differentiating. This is the derivative function here. So we started with what? We started with f of x being a times x to the power of n, and now it looks like that. So we're going to make a general rule out of this. All right, this is called the power rule in differentiation. What it is, the power rule is that when your y or f of x is a times this a is a constant, almost doesn't matter. That a remains as it is. You don't change that constant there. You just bring the power down. So let's omit a for now and write it in simpler terms. When f of x is x to the power of n, n being some integer, it's positive integer, but it can be negative as well. Therefore, the derivative function is just bringing the power down, means multiplying it by x at the front and subtracting 1 from it. Okay, you subtract 1 after you multiplied it as a coefficient at the front. Now, if there is an existing coefficient here, like an a at the front, then that remains unchanged. You leave the a where it is. You just need to multiply n by a, and so on and so forth. So let's make note of this rule, and we're gonna start using it in the next few examples. So let's see how it's used. We just make it we made a generalization here, and I hope you made a note of this. Okay, I did say f dash does represent dy by dx. These two are just name of the mathematicians who used calculus in different locations. They just were writing the same concept with just with different notations. Leibniz is the name of mathematician. Joseph Lagrange is also a famous mathematician. You should know. All right. So with this rule, now we're gonna put it to use. What is the derivative function of x to the power 6? Pause the video, have a go. Oh, you got this. 6x to the power of 5. I have done this so many times, I can do it in my head. What's the derivative of this function here? You bring the half multiplied by x and subtract 1 from half, leaves the power to be minus a half. So you write half in front of x to the power minus half, and you can rearrange this if you wish and put the x in the denominator. It's the same as this, okay? But the point is to get this calculation correct. So half minus 1 means if you're not familiar with, like, if you can't do this in your head, learn how to do it in your head. It's like subtracting 2 over 2. Okay, so that's how I got that quickly. After a few times you've done it, you should be able to do this quickly. Now that's just rewriting that through there. So what is the derivative of x to the power of minus 2? Minus 2 becomes the coefficient, and the new power of x will be minus 3 because you subtract 1. So minus 2 times x to the power minus 3, and you can rearrange and rewrite it like in the denominator with a positive power if you wish. Don't forget the minus at the front, okay? The power was a negative 2, so the coefficient is now a negative 2. Now, if you have to factor, like define the derivative here, first simplify it. Don't try to, when there's a multiplication there, you can simplify it and rewrite it with power rules first and then find the derivative, right? So look at the next example. Try to rewrite it as a single power of x and then have a go at it. So as a single power of x, it will be x to the power of minus 4 actually. So we bring a minus 4 at the front for the derivative. So don't be shy, write simplification as f of x, and then you bring the minus 4 at the front and subtract 1 from the power. So You could rewrite it with the x in the denominator if you wish. Next one, this is where you have a coefficient like that a is now a valid number. That a is 7, so you bring this 3 and multiply it by 7. You get 21, and then you subtract 1 from the power. And now, for this case, you're going to multiply half by -4. The coefficient of x will be a -2, and the new power of x will be x power of -half. You can rewrite that if you wish as a x in the denominator with the square root if you wish, but the point, as long as you get this right, I think that's most important. Now here are the questions from the next exercise. I don't want to show you the answers, so go look the questions up from your book, and I'll see you in the next video.